Okay, guys, we continue our talk. And the last time I showed you that this is the J integral. If we have enclosed, this is a contour around this is corrective, and this and the J will be equal to 0. And so this, in this sense, it means that so J is path independent if we have one single. This is the path around, and this is the corrective. And today here, so J is defined as this way, okay? And the counterclockwise, or here is a corrective, is a counterclockwise, and this is the path. We do the integral. This is omega. Okay, so this is omega dy. And so minus ti dui dx ds is the arc, right? The arc increment. And so this one can be written as we use this is the nx and the ny. So what is the nx ny? And because from the calculus, and we know that dx dy they are related to the ds. ds is arc, okay? So using these two equations, this nx is the nx, because the n is, what is n? And the n is the function of this point, the unit, this unit norm. And so this is the n, and this n can be decomposed into n1, n2, or, and we have nx and ny. So this is n can be decomposed into these two components. And so ds, dy, ds, dx, they are related using these two equations. And we just plug in. So this equation can be written in terms of this. This is tau sigma CCW is this corrective. I'm giving you this schematic. And the tau, okay? So there is a tau u, guys. What is the tau u? And this, I'm sorry, this is gamma, okay? This is gamma u, this is gamma. The gamma u is an essential boundary condition. And have you guys ever heard essential boundary condition? The gamma u, and gamma u is essential the boundary condition. So gamma t is a natural boundary condition. So this is called NBC. So this is called EBC. So what is TU? TU means that on this boundary, displacement is prescribed. So is a displacement is prescribed. So for here, is the traction is described. The traction is prescribed. You understand, guys? So, Maxim, you and Bobby, you took the FEM with me, right? So then we learned this is FU, this gamma u and gamma t. So u is in central boundary condition, and gamma t. No, I'm supposed to say u. Okay, gamma u means that this undistant parts, the essential boundary condition is prescribed. The gamma t means on these parts, and the traction is prescribed. Understand, guys? Traction and the essential boundary condition, they are two different concepts. So as we get here, and we are going to derive and how we this is a simplified is a J. So you can see the pi. Okay, pi is a potential energy for the whole body. So this guy equals the u. U is a straight energy. Yes, straight energy. whenever you do something to the body, they have elastic deformation. Then you have elastic strain. That means this guy is storing some energy. So this is called strain energy. This W is work done by external force. The work done by external force. How much work by the external force? External force here, and we are referring to the traction. This omega, okay, as I said last time, and when I wrote this using my hands, and the omega and W they are very difficult to write differently. But I just put this is capital W means this is capital W. So here is omega. So this is omega. Omega is the strain energy density. Strain energy density multiplied by dA. dA is area. Area multiplied density equals the energy, strain energy. You guys agree? You guys agree, guys? So I also told you, we just for simplicity, we assume the thickness is unit. Unit thickness with unit 1. Area multiplied by thickness is volume. And volume multiplied by strain energy density equals strain energy. Right? So this is the first term. And second term is related to the traction. You can see Ti, Ui. U is a displacement. Uti, Ui, this is a I is a dummy. Dummy means summation. Right? That means and Ti and Ti, Ui, I is a dummy index. So this one equals T1 multiplied by U1 plus T2 multiplied by U2 and plus T3 multiplied by U3. So, but for simplicity, we still use the initial notation, or this is Einstein notation. But then after we get this strain energy, and then we take the derivative of strain energy, and with respect to A, and as I said last time, okay, when we have derivative, when we have integration, the order does not change, right? So as a result, and for the first term, I just put the derivative sign, I'll just take the derivative of this omega, the integrand, and then do the integration. And for the same thing for the second term, I just put this derivative and take the derivative of the integrand, which is within these parentheses, and so this is the d pi dA. Now I'm going to talk about the second one. Okay, how to calculate the second one, and how to calculate the second one. Last time I told you guys, okay, so last time I told you guys, here is d Ti Ui, and so this is a multiplication of these two guys, and we can just do the derivative for this guy, and the first term, the first derivative multiply, copy the second term here, and then copy the first term, and then multiply by the derivative of second term, with respect to A. Then we have the parentheses. Are you guys okay with this step from here to here? You guys are okay, right? Okay, now this is ds. So dTi dA equals 0. Why this equals 0, guys? Because the traction does not change with the crack length. Write down, guys. Otherwise you might be confused. Why the dTi dA equals 0? Because Ti is a value. This guy is independent upon the A. As a result, this guy goes to 0. And this guy goes to 0. As a result, and the whole term disappears, and we only have the second term we have here, and we have here. So because this term we have is related to the T, right? That means for the gamma U, and everything equals 0. That's the reason. And for this is the this is integration is only valid for gamma t. For gamma u means that no traction. No traction means the traction is 0. As everything goes to 0. So any questions from this one to this? No question? No question, and then we just move forward. So this is the gamma t, right? This is gamma t. As I said, I just told you guys, the gamma u for t equals 0, right? For the gamma u, for on the boundary of gamma, on the boundary points where the essential boundary conditions are prescribed, and then natural boundary condition equals 0. So no traction. No traction, I just have another term, gamma u plus multiplied by this one, but I know this term equals 0. Let me write down. So I have this term, gamma u, and ti and dui and dA multiplied by ds. I know this guy equals 0, right? Because for the u, the essential boundary condition boundary, no ti equals 0. So I know this guy, the whole thing equals 0, because this guy is 0, and I can just end this 0 here. Do you guys agree? Why I need to do it? Because here is a gamma t. I want to have both gamma t and gamma u. What? Also here, dui dA equals 0. No traction, but also displacement does not change with A. And as a result, this for here, ti equals 0 and this equals 0, because ui is independent upon this is A. So that means this is 0, this is 0. Then gamma t plus gamma u is a whole enclosed the path. Whole enclosed path. Okay.
So that's just how you go, that is now the expression for the second part of the pi.
Yeah, second term. Yeah.
We just kind of change it into that form now. or-
Yeah.
Okay,
Well, changing. Okay.
okay,
So we have not talked about the first one.
Okay.
Yeah, but second one is most important.
that's what it is now.
Yeah. Yeah, 60 is the second one. I'm going to show it. Bobby, that's a very good question.
Yeah, I'm just trying to see how it fits into the.
Yeah, here. So this is this equals this term minus this term.
Okay.
And we will talk about this term first, okay? So that's the reason I write 2 here, 2 equals this. So any questions from here to here? No questions? No questions, and there is the mathematical manipulation, okay? So I hope you guys enjoy this. Very important, but very, very useful. Because here, okay, you can see D, dA, okay? And D, dA. So D something, this is operator. D something dA equals D, dA of this, right? Plus dx, dA multiplied by D, dx. Do you guys agree with this? So D, dA with respect, so this equals, right? And something and dA, the partial differential equation, right? And then I take the derivative again with respect to x. So this one, okay, I'm sorry, this one equals is a dx and dA d something and dx. So you can see this cancels this.
You have d over dA plus d over dA. Then if the two dx's cancel out.
So you can see here, So here is a crack, right? If this is a crack, this is the x, and so this is y, so this is origin. So this is A. You can see here, okay? A plus x equals constant. A plus x equals constant. And then you dx dA equals -1. dx dA equals -1. So this one, let dA something, and it equals this guy take the derivative of A, and plus this guy take the partial differential of the equation dx, then multiply by dx dA. So this is a partial differential equation. So you can see here, so I just said here, because A plus x equals constant dx and dA equals -1. And so as a result, you put a pi here, okay? And d pi dA and equals, let me put down. D pi dA here, okay? So dw dA. So here, dw dA, we will have, we just plug in dw here, we just plug in this w. This is w, so here is a w, and here is a w. So here is a -1. And then we will have dw, the partial dw dA minus and dw dx. And so this is our first term, dA. Then minus, so this is the second term, we just simplify. And second term equals this ti dui dA, also ui, okay? U here, and we put this ui here. So for this one, for w, and we also for ui dA equals d ui and dA plus here is a -1 multiplied by d ui and dx. And here is d dy dx. This is how we get it here. What? Questions?
Wait, what's the point of doing that?
We are going to do this because the UI, okay, UI, because the x is changing. X is changing. All right, you can see. Here, once we get here, we want to do calculate this part. So this part we have two parts, and we have so ti dui dA ds for the first part. For the first part, this is the enclosed circle, and we can use is ti equals sigma ij nj, right? You know that, right? how to get the traction from the stress. This is dui dA ds. So, and we use Green's theorem and to change this integral for this is the enclosed boundary and to the area. And I told you guys last time the Green's theorem. So this is xj sigma ij dui dA. So here is because this nj here, nj ds, it can be written as here. So it's based on the Green's theorem. After we get here, okay, so we take the derivative, partial derivative of the multiplication of these two guys with respect to xj, and we will have this guy multiplied by d sigma ij dxj multiplied by d ui, right? Just copy here, dui dA, then plus copy this guy, and then do the derivative of this guy with respect to xj. So we have d dxj dui dA. Then this is dA. So because sigma ij dij d sigma ij dxj and equals 0. Right? We know that, and this is the equilibrium equation sigma ij comma j and plus fi equals 0. And fi we just assume it equals 0 for simplicity. As a result, at sigma ij comma j equals 0, sigma ij comma j equals d sigma ij and dxj. Common means the derivative. So because this is equilibrium, we know that this body is in the equilibrium. In equilibrium means that body does not rotate, the body does not translate in the state of equilibrium. So this guy equals 0, so this is gone, and then we have sigma ij dxj dui dA. We only have this term. You understand, guys? And from here and to here, we also use the rule that when we have the derivative twice, the order does not matter, right? We just change the order, and we do the derivative of dui dxj first. And dui sigma ij dA, and because sigma ij is symmetric, we know sigma ij equals sigma ji, and so we can have sigma ij, and so this is dui dx is 1, and dui dx equals epsilon ij. epsilon ij. Epsilon ij equals u comma j plus u j comma I. 1/2. The sigma ij is equals sigma ji. So this is the epsilon, right? This is epsilon, and this is epsilon dxj dx dui dxj equals epsilon ij. So we have here. And then we know sigma ij, okay, sigma ij equals the energy density, omega is energy density, E epsilon ij multiplied by this guy, and then this guy cancels this. So we have E omega dA dA. Right? Now we conclude that, you can see this guy equals this. You can see dw d omega dA d capital A, d omega dA d capital A. So that means the 2 equals 1. Now we conclude that, so this part equals this part. What does that mean?
equals 0 then?
Yeah, d pi equals 0. Questions so far? Now this equation star, okay, so this equation star here can be simplified as equation here can be simplified as this one and plus this, and then here so this is so equation star here and d omega dA d omega dx. So this guy can be simplified as here we just simplify this one dui dui dx and d omega dx. So this one equals omega dy plus this phi. This is gamma ti dux dx. This equals minus j. So this is minus j. J equals d pi dA. Okay, and j equals d pi dA. And please note that so this is for the plus b plus gamma c, and this is the b, the gamma c. And we do not use the gamma c, okay? We do not use gamma c. Gamma c equals 0. And we only have this is gamma b. So this is how we calculate this j here. And I want you guys to take a look at how I derive this equation star. Questions? Okay.
So does it equal 0 then, or was that just?
So equals 0, that means we need to have two boundaries, closed one. Now we just only have one. This is one parse. What? One parse. So this one we use. This is derived as a j, and so this one is consistent with what we have talked about the last time. For the following stress-strain relationship by this equation. So this is a Ramberger-Osgood equation. So this equation, okay, so this is a stress-strain relationship. Epsilon is the strain and sigma is the stress, epsilon 0 and sigma 0, and they are reference stress value and strain value respectively. And so this alpha is a dimensionless constant, this capital N is a strain hardening component. So for this one, and we have HRR proposed, this HRR method, and sigma ij equals sigma 0. And so there is a lot of equations here, and sigma ij with and the dimensionless function of n and theta. And n is the strain hardening components, and theta is the orientation. Also, epsilon ij equals this one, okay? So this is from HRR. And we just take a look at the leader term. For leader term, sigma ij is proportional to the r minus 1, n plus 1, epsilon ij equals r minus n plus 1. However, for linear elastic fracture mechanics, n equals 1. So that's the reason we have sigma ij, it is proportional to r minus 1/2, epsilon ij is proportional to 1 r minus 1/2. So this is consistent with what we have learned for LEFM, right? You guys agree? Okay, so this is series. If this one LEFM is a special one, n equals 1, and that you can see, so HRR can accommodate this LEFM. So you can see sigma ij is a singular when r goes to 0, and epsilon ij and is also singular, and 1r goes to 0, right? You still remember, guys? And in the LEFM, and we know that sigma ij goes to 0. Sigma ij is singular. Singular means goes to infinity. 1r goes to 0. And epsilon ij goes to infinity. And singular 1r goes to 0. But ui is not. You still remember, guys?
Yes, yes.
Yeah, u is proportional to r 1/2. That means when r goes to 0, u goes to 0. So that's the reason ui is proportional to r 1/2. So when r goes to 0 and u goes to 0. So this is u is not singular. So this is in here. In we have these two equations for plane strain and plane stress, respectively. And for the j, okay, for j, and is defined as this equation minor equals negative d pi dA for nonlinear elastic small string. So, however, if larger string are used, the crack becomes blunt and then reduces the stresses, and then we will have triaxiality. So here, look at this curve. So at the very beginning, delta CTOD, crack tip opening displacement. So this is a normalized sigma yy. So here is a curve, it is HRR singularity. So here is a large string analysis, this solid one. So this is a stress field influenced by crack blunting here. So here is x sigma 0 divided by j. So this is normalized relationship between sigma 0 and sigma yy. So look at here for free surface, sigma xx equals 0. Okay, for this crack is a blunt, and from 0 to 2 delta, stress goes down, and sigma xx goes to almost 0. When x is greater than 2 delta, and HRR is okay. You can see when x, the displacement from the point of interest to the crack tip x is greater than 2 delta, and we can use HRR. Any questions regarding this one? So there are a lot of equations. I'm sorry, guys, it's kind of boring, but I would like you guys to take a look. Okay. So remember, guys, what does this figure say? It says that when the x is greater than 2 delta, and you can use HRR to determine your sigma ij using the j value. I will not test your derivation. No worries. Okay. Questions so far? No question. I'm going to end today's session. I want to recap what we have said. By this Wednesday, finish the modeling of this handout. By this Friday, finish the first model of our mini project. By next Monday, finish our second model of the mini project. I will check all these three milestones at the very beginning of the class. Then next Monday, I'm going to show you how to do the post-processing. By next Wednesday, and you finish the mini project. Okay. So I hope you guys have a wonderful Monday.
Thanks, Dr. Moore.
You're welcome.
A lot of equations.
Yeah, a lot of equations. Yeah. Yeah.
I was in here Friday. I think I put it on.